In this part of dynamics, we're going to take a look at connected particles. Now these are probably the most difficult problems you're going to encounter in M1. They're going to make use of all of the skills you've picked up so far in this chapter. And it's very important to make sure that you label all of the forces involved. Now, if your particles are acting in the same direction, if each part of the system is moving the same straight line, we can consider the system as a whole, and we can treat it as just one particle, using all of the forces on one side, and all of the masses added together on the other side, times acceleration. However, if they're moving in different directions, as is often the case with pulleys, then we can only consider each part separately. In either case, the acceleration is going to be the same for all parts of the system. So we want to make sure we always resolve forces taking the direction of acceleration as positive. If we don't do that, then we're going to make a big mistake. So let's take a look at a couple of examples. In this example, we've got two particles connected by a piece of string. We're told what the mass of each particle is, and one of those particles is pulled along by a force of 40 newtons. And we are on a rough horizontal plane, so we are going to need to take into account friction. Now this sort of problem is fairly typical of a connected particles question. You might see it modelling things like cars pulling a caravan or something like that. So, as usual, we want to start by drawing a diagram. We have our 40 Newton force pulling the whole thing along. We have a reaction force, which I'm going to call Rp in this case, since it's on particle P. We have the weight of that particle pulling it down. And we have friction trying to resist its motion. We also have the tension in the tension in the string acting here. For particle Q, we've got the tension in the string pulling it along. We have the reaction force, which I'm going to call Rq this time. We have its weight. And we have friction. So, first we want to find the acceleration of the whole system. Since they're connected by a string, this is going to be the same for both particles. But since we don't know what that friction is, we want to figure out what the reaction force is first, and then find friction using the coefficient of friction. So, if we resolve vertically for P, we get Rp minus 5g is equal to 0. So then we know the reaction force at P is equal to 5g. Doing the same for Q, we find that Rq minus 3g is equal to 0. So then Rq is equal to 3g. So then we can resolve forces horizontally, and keep in mind that the coefficient of friction is 0.2. So resolving now for the whole system, we have 40 minus Fp minus Fq. We would also include our tension, but we'd have plus T minus T, so they'll cancel out. Any internal forces for a connected particle system will cancel out. But we label them because we'll make use of it in part B, where we're actually trying to find that tension. And since we're doing the whole system, we'll need to add the masses together. So we have 8a. So then we have 40 minus 5g times 0.2 will give us just g, and then we have 3g times 0.2 will give us 0.6 g. Our tensions will cancel, and we're left with 8a. So now we can just work out what we've got. We have that 8a is equal to 24.32, and then we can divide by 8, so we get that A is equal to 3.04. And since we've made use of G, we might want to round that to two significant figures, so 3.0 meters per second to 2 SF. Now for part B, we're asked to actually find the tension in the string. Now we could resolve forces around P, or we could resolve forces around Q, and we want to consider just that particle, whichever one we do. Now in this case I'm going to choose particle Q, so if I resolve horizontally for particle Q, we've got T minus FQ is equal to 3A. So here we only have the mass of Q coming into the equation. So that tells us that T minus 0.6 G is equal to 3 times our 3.04. Now we want to use the true value, not the rounded value that we found. So then that tells us that T is equal to 9.12 plus 0.6 G. So then T is equal to 15 newtons. And we are done with this example. Now because we had each particle acting along the same line of action, we were able to consider the system as a whole. Now let's take a look at another problem where they're not all acting in the same direction. So in this problem, we've got three masses, each connected by light inextensible strings, and they're running over pulleys so we can change the direction of motion. Now since they're different strings, we get different tensions acting. We're also told that the mass of M1 is larger than that of M3, so that suggests that M1 is going to accelerate downwards, and that's going to cause M3 to accelerate upwards. So let's scroll down and take a closer look at this diagram. We have a number of forces acting here. Now we've already established that the acceleration is likely going to be down in this direction because M1 is heavier than M3. So that means that M2 is going to be pulled over to the left and M3 is going to move up. So this is why it's important to always make sure you resolve your forces taking acceleration as positive, because in each part of the system we've got acceleration acting in a different direction. But of course before we can resolve forces we need to draw them onto our diagram. So we have the weight of M1 and the tension, which I'm going to call T1 in this case, and we have T1 that's pulling M2 along, we have T2 that's trying to slow it down, we have a smooth surface so we don't have friction to deal with, we've got a reaction force, and we have the weight of M2. And then over here we have T2 pulling M3 up, and we have its weight pulling it down. So now that we've got all of our forces labelled on the diagram, we can start resolving forces and writing some equations down. So, starting with M1, we want to take down as positive. So we have M1G minus T1 is equal to M1A, because we're just considering what's happening to M1. Then, looking at M2, we want to take left as positive. So we have T1 minus T2 is equal to M2A. And then for our third particle, we want to take up as positive. And this is an important difference. If we had taken down as positive, then our equation is going to end up being wrong. So we have T2 minus M3G is equal to m3a. So that's part A done. We've got our equations of motion. For part B, we're actually told what the mass of each of these particles are. So we have that we got 8g minus t1 for our first equation. We've got t1 minus t2 is equal to 10a for our second equation, and t2 minus 5g is equal to 5a for our third equation. And what we're trying to find here is the acceleration of the system. We've got three equations and we have three unknowns, t1, t2 and a. So if we can eliminate t1 and t2, we'll have just an equation in a. So if we use our first and third equations to get something in terms of t1 and t2, then we can substitute into our second equation. So we get that 8g minus 8a is equal to t1, and then we also have that t2 is equal to 5a plus 5g. So that's going from this equation and going from this equation. Just rearranging these equations at this point. Now that we've got an expression for t1 and t2, we can substitute into our second equation. So we then get 8g minus 8a minus, in this case it's worth making use of brackets so you avoid making a mistake, 5a plus 5g is all equal to 10a. So we can then expand our brackets, and then we can start collecting terms. So we end up with 3g on the left side, and we get 23a on the right hand side, because both of those negative a terms will become positive as they come over to the right hand side. So we have that 23a is equal to 3g, so then we can divide by 23, we find that a is equal, let's bring this over here. So a is equal to 3 over 23g, so then a is equal to 1.27, and hence, since we've made use of g, we want to round to two significant figures, we have 1.3 meters per second to 2sf. So that's how we can deal with a problem where we have our system, parts of our system acting in different directions. So if you're happy with that, have a go at exercise 3F. Or if you're feeling very confident, have a go at these questions.